As you know, I'm not here today, and I wanted to go over a few of the homework problems with you and remind you that we do have a quiz tomorrow, and so make sure that you prepare for that quiz. Yesterday we were talking about finding local max, local mins, increasing and decreasing intervals, and so I'm just going to take problem number 1, and it's asking you use the graph to find the largest open interval on which the function is increasing, and of course this is the original function, so all you're looking for is when the graph is going up. So the largest open interval would be this interval right here where the graph is increasing. That's not the only increasing interval, but that would be from 0, close on the endpoint, to 6. And then the largest decreasing interval, there are two decreasing intervals, but it increases over the largest interval, it looks like from 6 to 8. So that's a pretty easy problem to work with. But I mainly want to get to the other problems that's going to involve more algebra. So let's take a look at, I highlighted a few problems that I wanted to look at. Problem number 22, I'm not going to do, 23, I'm sorry. I'm not going to do problem 23, but I just want to remind you that when you're finding the first derivative, to make sure that you use your algebra, sprinkle your algebra, and you get 3x squared minus x cubed, and then use the power rule to find the derivative. In number 25, I wanted to remind you to, again, sprinkle a little algebra. This is the same thing as 1/5 x to the 5th minus, because I'm dividing everything by 5, 1x, and then just use the power rule, and then you have a pretty easy problem to deal with. The problem that I actually kind of want to walk you through is problem number 35, because it involves quotient rule, and also because you get a place where the derivative is undefined. So in problem number 35, once I find the derivative, and the derivative I would find by the quotient rule, so you know we would have down d up minus up d down over down down, and you would clean that up, and your first derivative turns out to be 18x over x squared minus 9 quantity squared. So that's your first derivative, and you know that you're going to take your first derivative and set it equal to 0 to get your critical numbers. So in this case, if we set that equal to 0, we get a critical number of x equal to 0 out of the numerator, but in the denominator there are two values of x that will make the derivative 0, or that will make the derivative undefined, and that's positive 3 and negative 3. So these three guys are your critical numbers, and they're going to go on your number line to divide your number line into regions. Don't forget to name your number line first derivative, and the first derivative is going to reveal things about the original function. So I put my critical numbers on my number line, negative 3, 0, 3. Now remember, we're going to choose a value out of each interval, and we're going to substitute those values into the first derivative. So I'm going to use my first derivative, which is right here, to substitute those values. So for example, also notice, let me go ahead and say this, notice that in this case that the denominator will always be positive because we're squaring. So the numerator is going to determine the outcome of whether we get a positive or a negative. So let me change colors here, since we're now talking about the original function. If I pick a value like negative 4 and put it into the numerator, I'll get a negative divided by a positive, which is a, I'm sorry, if I put negative 4 into the numerator, okay, what I just realized is that the derivative is a negative 18x, because that was going to mess me up. So sorry about that. So back to what I was saying. If I pick negative 4 and I put it into the numerator, I'll get a positive divided by a positive, which is a positive, which tells me that the original function is increasing. Likewise, when I pick a number between negative 3 and 0, I'll get a positive. And when I pick a number between 0 and 3 and substitute it into the first derivative, I'll get a negative. So the function decreases. And likewise, when I pick a number from 3 to infinity and substitute it, I'll get a negative. So we see easily on this graph that there is a local maximum at x equal to 0, and it is f of 0. I'm not going to write that all up because I want to save time to do another problem. You can see your increasing intervals are here and here. Your decreasing intervals are here and here. And so then you would write that up. All right, one more problem that I would like to take a look at, and then I'm going to remind you of the things that are on your quiz for tomorrow. Problem number 39. Now, when I did this problem, you can see that we're going to have to do the product rule one way or the other. And when I did this problem, I went ahead and, for whatever reason, I distributed the e to the x minus 3. It doesn't really make it better or worse. 3e to the x minus 3 by distributing, and minus x e to the x minus 3. Now, that's the original function. When I find the first derivative, the derivative of the first term is 3e to the x minus 3. Remember that the derivative of e to a power is e to the power times the derivative of the power. For the next term, I'm going to have to use the product rule, and so that would be first times the derivative of the second plus the second times the derivative of the first. When I distribute the negative and I combine like terms, I have a 3e to the x minus 3 minus e to the x minus 3, which gives me 2e to the x minus 3 minus x e to the x minus 3. And if you need for Mr. Albertini to stop the video and for a second, you are welcome to do that. I'm going to set the derivative equal to 0, and I'm going to factor out an e to the x minus 3, which leaves me with 2 minus x, because both terms have an e to the x minus 3. Now we're going to set each factor equal to 0 to find my critical numbers. Now remember that e to the x minus 3, e to a power, can never equal to 0. So e to the x minus 3 is never equal to 0, and you don't get a critical number out of that. So the only critical number that you're going to get in this case is x equal to 2. So that's your critical number, and that goes on to your number line. So I'm going to change colors here. Hopefully that changed colors. Name your number line, first derivative, and put your critical number on your number line. Choose a value in each region to substitute. Now take a look. Right here is where I would substitute in the factor stage. E to a power is always positive. So I'll say that again. E raised to a numeric power is always positive. You can't get a negative out of that. So we know that no matter what, we're going to get a positive multiplied. So the 2 minus x determines the outcome. So if I choose a number to the left of 2, like 0, and substitute it, you can see that the outcome will be positive, which tells me that the original function will be increasing. And if I choose a number larger than 2, like 3, the outcome will be negative, which tells me that the function is decreasing. And so you can see that I have a local maximum occurring at x equal to 2, so I'll write this one up. Local max at, this is how I want you to write it up, x equal to 2, and is f of 2 because first derivative changes from, I'm just reading the graph, positive to negative at that value. Okay, so that's two problems kind of representative of what you were doing. Each problem has its own little twist and turn, and you can ask questions of each other and help each other out with any of the other problems that you looked at. You've got the solution manual, you've got Patrick videos, and of course I'll be back tomorrow, so if you have any questions you would want to come before school. Today in class you're going to work on more of these problems, so you're just going to have time to think about all this. So for the quiz tomorrow, oops, one more page. For the quiz tomorrow, you need to still remember your inverse trig derivatives. That'll be a recyclable. Derivatives of inverse function. Remember, I gave you a video on that. Make sure you understand how to do that. Symbolic derivatives. These three guys kind of work together because I could give you any of it as symbolic. For the three theorems, make sure that you know the conditions. Make sure that you know the promise for each theorem, and make sure you know how to apply, actually do problems with each theorem. Okay? And then finally, the first derivative test is exactly what we were just doing in the homework and that you're going to practice again today. So anyway, it should be a pretty straightforward and easy quiz, and I will see you tomorrow.